Right, so where were we? Sorry, it stopped then because I only get 15 minutes on my NAF free screencast-o-matic software, which I have not bought because I thought college that should buy it for me, but they didn't. So, here we are. Anyway, series and parallel resistance rules. So, you do need to be able to derive them, as I just said. You need to know why you can derive them like you do. So, the key idea behind the series is that current through each resistor will be the same. So, if you put V over I, and I is constant, so V voltage would be voltage 1 plus voltage 2 plus voltage 3 plus voltage 4. That would be total voltage, wouldn't it, in a series setup? Then, because of Kirchhoff's second law, then you'll end up with V1 plus V2 plus V2 over I, and you'll get V1 over I plus V2 over I2 plus V3 over I3, which are all the same thing anyway. So you'll get R1 plus R2 plus R3, and that's the rule for resistance equivalencies. For the parallel one, the voltage is the same across each resistor. That's the key idea. And so we can say, well, the voltage is constant. Voltage over resistance equals current. So current 1 plus current 2 plus current 3 equals voltage 1 plus over resistance 1 plus voltage 2 over resistance 2. And if voltage is constant, we just get 1 over, don't we? So 1 over resistance total is equal to 1 over resistance 1 plus 1 over resistance 2. If that makes sense, amazing. Science. Right. Then we've got potential dividers, the easiest thing on the planet, right? It's simply a case of what share of the total resistance does your resistor have? It's got R over total R1 plus R2, and then you just times that by the total input voltage, and that's your output voltage. They're really quite useful, and you can get the potential dividers, sometimes called potentiometers, where it's like one whole length, and then you just select what length of that you are choosing, and the length of it that you have chosen, like to straddle, will give you an output voltage, which is a direct proportion as the length is of the total length. So let's say you choose half of the length, you'll get half the voltage output. If you choose 3/4 of the length, you'll get 3/4 of the voltage output. Science. Then we've come to internal resistance of a cell. Right, this was the fun bit. Right, you've got a cell. It looks like it gives an output of it should give an output of 5. Let's say it gives an output of 4.5. You're like, where's that lost volts come from? Well, inside the cell, between the terminals, there's internal resistance inside that cell. So we talk about terminal potential difference, which is the potential difference between positive and negative terminals of your cell. And then we talk about EMF, which is the theoretical supplied maximum, which is sort of imaginarily inside the cell. And then we've got our lost volts as well. So we can say our terminal potential difference is equal to our EMF minus our lost volts. And we can get the V equals epsilon minus Ri equation out, provided for you as well. Don't worry about that. So just you can do various rearrangements of that. E equals V plus IR, E equals I times big R plus little r. Loads of different versions of that, and you're all capable of dealing with it. What's cool is that if you carry this experiment out like this, and you just change this external resistance and measure the terminal potential difference, you get a weird outcome, which is that, right? So each time your external resistance goes down, your current goes up in the circuit, but the terminal potential goes down. That's because, just like in a potential divider circuit, your external resistance now represents less of the share of the total resistance, so it gets less of the potential. Now, yeah, sorry, my little girl is standing at the top of the stairs, and I can't remember how to get her. Where was I? Right, so yes, you just like any potential divider, you've got the simple setup that if you change the proportion of your resistance, how it represents a total of the whole. So let's say external resistance drops. It means that if you imagine it as a large resistor and the small resistor at the side of it, then if this one's resistance drops, this one now represents a larger proportion of the whole and will get more of the potential than it just did. So that is increasing the number of lost volts, right? Which means it reduces the number of terminal potential volts. So it goes down like that. If you use this equation as a y equals mx plus c graph, or in this case, y equals c minus xm, you'll get the gradient as the lost faults, and you'll get the intercept as your EMF value. This is useful, and you need to be able to do it. Then we've got the last thing on the list, which is sensor circuits, right? These are basically just potential dividers with a semiconductor in them, i.e. a thermistor or an LDR, right? So if you've done loads of these where we got, you just calibrating it. I gave you a little piece of graph in its NAF format, and then you used the 1/over relationship to make a straight line graph, and then you did it, you solved it from that point on. So you've done a few of these, and I'll try and chuck a couple of those into the questions that I set you. But yes, so a sensor circuit is just one way you can calibrate data with known values to work out unknown. So for example, in this, got a potential divider with a thermistor and a fixed resistor. The fixed resistor never changes, hence the word fixed, and the thermistor is a negative temperature coefficient thermistor, which as its temperature drops, the thermistor's resistance increases. So this can then be used which would then increase the output voltage. Now, what you could do is calibrate the output voltage to temperature and then use this as a temperature probe. They're really quite cool, aren't they? It's quite simple, and you can use them in a whole host of different settings. A proper sensor circuit has a lot more to it, but this is a simple sensor circuit. Right, that's everything. That is all of electronics, unless I've missed a massive gaping bit, but I don't think I have. Other than just to, you should know. There's loads of little bits, aren't there? But you should know them. The key bits are what we've covered, as well as a little extra bit, which is I think I've just remembered to say now, which is the N number associated with semiconductors, conductors, and insulators. And like 10 to the 28 is a good conductor. Less than that, significantly less than that, is a poor conductor, or even worse would be an insulator. But yeah, all of that stuff is just the detail that you should know, right? But hopefully we've covered all the basics there and reminded you of what's in electronics. Get revising it using the booklets that I send and have already given you, and do the questions that I send you, please, as well. I will also send a copy of this PowerPoint if it's in any way useful. I don't know. It's actually quite basic. I just sort of bashed it together just to give me some structure for talking to you. Also, I just wanted to talk to you, even though nobody's responding to me. I'm going a bit mental only talking to toddlers. You're probably noticing that. Not that I was massively sane beforehand. Right, okie doke. Happy lockdown. And hopefully I'll see you again at some point in the future.